In this video, we will learn how to run TopHat 2, specifically discussing important considerations for running TopHat, as well as going over the general command line setup. We will also discuss the different files that are output by TopHat. One important thing to note about TopHat is that it has several dependencies and requires that both Bowtie and SAMTools be in your path, meaning that you must load both a SAMTools and Bowtie module when you load the TopHat 2 module. There are version compatibility issues between these programs, and only certain versions of SAMTools and Bowtie will work with specific versions of TopHat. Complicating the issue, not every version of TopHat explicitly states what versions are compatible, nor do we have every version of TopHat, Bowtie, and SAMTools on the compute clusters. The job script that we will run in class will serve as a reference for suitable version compatibility between TopHat and its dependencies. In TopHat 2, you have the option to run either Bowtie or Bowtie 2, though Bowtie 2 is the default. Please be aware that when TopHat 2 runs Bowtie 2, it will only run it in the global end-to-end alignment mode. Although not every Bowtie customizable parameter is available when running TopHat, you will be able to specify a number of alignment options, including the various preset alignment parameter settings from Bowtie 2, such as fast and very sensitive. When running TopHat 2, you should also include regroup information in the command line, as this will be necessary for downstream analyses. Lastly, TopHat 2 has numerous options for customizing your run, each with a default setting, so it is very important that you take the time to carefully read through the manual. When running TopHat, be sure to give yourself plenty of time. It is not uncommon for TopHat to take several hours to run when mapping human RNA-seq data. Note that you do, of course, have the option to parallel process using the -p option. Before running paired-end library samples through TopHat, you must also have a good estimate of the average insert size of your library, as well as the variance or standard deviation in the insert sizes. Lastly, before running TopHat, you must also create a Bowtie index of your reference genome using the Bowtie build command. And as always, your index must be compatible with the version of Bowtie that you choose to run with TopHat. The general usage statement for setting up your TopHat 2 command is shown here, where after typing TopHat 2, you can specify any settings, after which you must specify the reference genome index name and provide the name of your RNA-seq FASTQ file. For paired-end data, you must provide both the forward and reverse reads in a comma-separated list, as we see here. Again, in the case of running paired-end data, you must include the average length and standard deviation of your library insert sizes using these parameter options here. And as one last reminder, don't forget to include the regroup header information using these options that are shown here. Because there are so many options for customizing TopHat, I'm not going to go over every single parameter that can be included in the command line. Instead, I'm only going to focus on one scenario in which you map reads only to known transcripts and skip any de novo or novel splice site discovery. In this particular scenario, you would want to disable coverage island assembly with the no coverage search option, as well as turn off novel junction discovery with the no novel junks option. You will also have to specify a set of gene annotations using the -G option, followed by the path and file name of that annotation GTF file. You must also explicitly tell TopHat to only map to the transcriptome using the -T option. Lastly, one option I suggest that you always include in your TopHat command, particularly if you have longer read lengths, is the micro exon search option, which enables TopHat to find alignments spanning extremely small exons. Running TopHat with these options will likely be the quickest way to align your RNA-seq reads, and to speed things up even more, especially when running multiple TopHat jobs, you can index the transcriptome a priori and save it in a separate location, just like you would a genomic index. If you do not build and save a transcriptome index separately, then TopHat will have to perform this step for every single run, which will take additional time. The last thing that we will discuss in this video is the output from TopHat. TopHat will create several output files in addition to many temporary files. TopHat will automatically output these files to a separate directory. If you do not specify a directory for this output to be written to, TopHat will automatically make a new directory in your current work directory that's named TopHat_out. I suggest that you always specify a unique directory for the output of TopHat to be written to. To do this, you must first make this directory before running TopHat and denote the location of this directory using the -o option in your command line. When aligning multiple RNA-seq samples with TopHat, you should give these specific directories unique names that are specific to each of the samples, because the files that are generated by TopHat will be ambiguously named. Specifically, the files that TopHat will output will be named accepted_hits.bam, which contain the alignment information for all mapped reads, as well as a BAM file containing the information of unmapped reads. TopHat will also generate a bed file annotating all the junctions that it discovered and was able to align reads to, in addition to generating 2 bed files denoting the location of insertions as well as deletions. Depending on your particular experiment, you would then select one or more of these files to move forward in your analysis pipeline. If you are interested in quantifying gene expression, as we will be discussing in the next video, you would use the accepted hits.bam file.